Right now, as you watch this, an object is drifting away from our solar system at over 210,000 kilometers per hour. It did not come from here. It was not born in the same cloud of gas and dust that formed our sun, our Earth, or anything we have ever studied up close. It came from another star system entirely, and based on the chemistry locked inside its frozen core, it may have been traveling through the galaxy for 12 billion years. That is nearly 3 times older than our entire solar system. And on August 6th, 2025, the James Webb Space Telescope turned its infrared eye toward this visitor and captured its first spectral image. What Webb found inside the glowing shroud of gas surrounding it broke nearly every assumption we had about what interstellar comets are supposed to look like. The carbon dioxide pouring off this thing was roughly 8 times more abundant than the water vapor. That ratio is among the highest ever measured in any comet, anywhere. Not a solar system comet, not a laboratory prediction, any comet period. But here is the part almost nobody is talking about yet. The deuterium locked in that water, the heavy hydrogen, was measured at more than 30 times the level found in comets from our own solar system. That single number rewrites the story of where this object came from and what kind of star system built it. And then there is the methane. But we will get to that. Stay with me because this story gets stranger at every step, and it is still unfolding right now. Subscribe now if you want more stories like this because we are just getting started. Let's go back to where this story actually begins. July 1st, 2025, the Atlas Survey Telescope in Rio Hurtado, Chile, was running its routine scan of the sky, looking for asteroids that might threaten Earth. The system flagged a faint object moving against the backdrop of stars. Within hours, astronomers pulled up pre-discovery images from the Zwicky Transient Facility and found it had been lurking unnoticed in data going back weeks. When they calculated its orbit, the numbers did not make sense for anything born in our solar system. The eccentricity came back at 6.14. For context, a perfectly circular orbit has an eccentricity of 0. An elliptical orbit, like most comets we know, sits below 1. This thing was at 6.14. It was not orbiting the sun, it was passing through. It was immediately designated 3I/Atlas, the third confirmed interstellar object ever detected. The first had been Oumuamua in 2017, that strange elongated body that showed no coma and accelerated in ways nobody could fully explain. The second was 2I/Borisov in 2019, which looked far more like a traditional comet, but still carried unanswered questions about its chemistry and origin. Now, a third visitor was falling inbound toward the sun, and this time the most powerful space telescope ever built was ready and waiting. The comet was active early. NASA's TESS satellite found it was already outgassing as far back as May 7th, 2025, at a distance of 6.4 astronomical units from the sun. That is well beyond the orbit of Jupiter. Most solar system comets stay dormant until they are much closer. Something inside 3I/Atlas was volatile enough to start boiling off in the faintest warmth of distant sunlight. That alone made it unusual. What came next made it extraordinary. On July 21st, 2025, the Hubble Space Telescope locked onto the comet from 277 million miles away. The image revealed a teardrop-shaped cocoon of dust surrounding the nucleus. Hubble could not see the solid core directly, but astronomers used the brightness profile of the inner coma to estimate the nucleus size. The upper limit came in at 5.6 kilometers across. The lower end sat around 440 meters. Somewhere inside that range was the frozen heart of an object that had traveled farther than anything we have ever studied. But it was not Hubble that would crack the real story. It was Webb. For decades, our models of comets assumed a basic chemistry. Water ice dominates. As a comet approaches the sun, that ice sublimates, creating the bright coma and the streaming tail we all recognize. Carbon dioxide plays a secondary role, and other volatiles contribute in trace amounts. That is how it works in our solar system. That is how every textbook describes it. Then Webb pointed its near-infrared spectrograph at 3I/Atlas on August 6, 2025, when the comet was still 3.32 astronomical units from the sun. The spectral images spanned wavelengths from 0.6 to 5.3 micrometers, and the data that came back forced a complete reassessment. The coma was dominated by carbon dioxide, not water, carbon dioxide. The CO2 to water mixing ratio came in at 7.6, plus or minus 0.3. That is not a modest elevation. That is 4.5 standard deviations above the trend line observed in long-period comets and Jupiter family comets across our entire solar system. The only comparable outlier was a peculiar comet called C/2016 R2, and even that comparison barely holds. The team, led by Martin Cordner at NASA's Goddard Space Flight Center, published the results in the astrophysical journal Letters. They also detected carbon monoxide, water ice, dust, and a tentative signature of carbonyl sulfide. But the CO2 signal overwhelmed everything else, particularly the 4.3 micrometer band, which was exceptionally strong. Now stop and sit with that for a second. Every comet we have studied in detail from our solar system has water ice as its primary volatile. This object, built around a completely different star, was running on carbon dioxide. The ratio was not just different, it was categorically outside the range of anything we have measured locally. To put that in perspective, the median CO2 to water ratio measured in solar system comets is about 17%. The mission-integrated value for Comet 67P, the one the Rosetta spacecraft orbited and landed on, was 7%. 3I/Atlas came in at 760%. But here is the part of this that stops being abstract and starts being personal. Comets are not just pretty streaks in the sky, they are delivery vehicles, the leading theory for how Earth got its water, and potentially some of the organic building blocks of life, involves comets and asteroids bombarding our planet billions of years ago. Every interstellar comet we study gives us a window into the chemistry of a completely different planet-forming environment. If 3I/Atlas formed in a system that was colder, more heavily irradiated, and chemically distinct from ours, then comets in that system were carrying a different chemical toolkit. The organic molecules detected in 3I/Atlas's coma, compounds bearing carbon, hydrogen, nitrogen, oxygen, and sulfur, show that the volatile building blocks for life as we know it were abundant even in that distant ancient disk. Martin Cordner put it plainly when discussing the results. He said, "The findings show that despite a cold and distant origin, the ingredients for life were present in this star system. We do not yet know exactly what that means for the frequency of habitable worlds across the galaxy. But the fact that we now have direct chemical evidence from another planetary system's leftover building material is itself a shift in what we can ask and answer." Then came October and the story got bigger. On October 3rd, 2025, 3I/Atlas made its closest approach to Mars, passing within 29 million kilometers. That flyby gave NASA a chance to do something unprecedented. The Mars Reconnaissance Orbiter rotated away from the Martian surface and pointed its Hi-R-C camera upward. This camera was designed to photograph rocks and craters on Mars at centimeter-scale resolution. Now it was aimed at an interstellar comet 30 million kilometers away. The image it captured showed a glowing coma spanning roughly 1,500 kilometers in diameter. Meanwhile, NASA's MAVEN orbiter used its ultraviolet spectrograph to image the comet's hydrogen envelope. And on the surface of Mars itself, the Perseverance rover pointed its Mastcam-Z skyward on October 4th and caught a faint smudge against the stars. 3 different NASA assets at Mars, all photographing a visitor from another star system. Think about what that engineering coordination actually looked like. But then the comet disappeared. On October 21st, 2025, 3I/Atlas passed into solar conjunction, slipping behind the sun from Earth's perspective. Ground-based telescopes went blind. This was the worst possible timing because the comet was approaching its most active phase. Perihelion, the closest approach to the sun, came on October 29th, at a distance of 1.36 astronomical units, just inside the orbit of Mars. The moment of maximum heating, maximum outgassing, maximum potential for structural change, and we could not see it from Earth. But NASA and ESA had spacecraft in position. The SOHO Solar Observatory, the Stereo A Heliospheric Imager, and the newly launched Punch mission all captured images of 3I/Atlas as it swung around the sun. The data showed rapid brightening and something unexpected. The comet's color was shifting bluer than the sun itself, suggesting changes in the composition or grain size of the dust being ejected. And the critical question on every astronomer's mind through those weeks was simple: would it survive? If you are the kind of person who wants space stories explained clearly instead of buried under jargon, go ahead and drop a like on this video right now because it genuinely helps this kind of content reach more people who would enjoy it. It survived. 3I/Atlas emerged from perihelion intact. No fragmentation, no catastrophic breakup. By early December 2025, it reappeared in the pre-dawn sky, and telescopes around the world swung back toward it. On December 19th, it made its closest approach to Earth at 270 million kilometers, roughly 1.8 astronomical units. Not close by everyday standards, but close enough for the most powerful instruments humanity has ever built to do extraordinary work. And the post-perihelion data deepened the mystery. Hubble observations from late 2025 and early 2026 finally allowed astronomers to separate the faint glow of the solid nucleus from the surrounding coma. The refined measurement published by Man-Tahui and colleagues placed the nucleus diameter at approximately 2.6 kilometers, with an uncertainty of about 0.4 kilometers. That makes 3I/Atlas significantly more massive than 2I/Borisov. But it was the Webb Telescope's December 2025 observations that delivered the next revelation. For the first time, astronomers detected methane in the coma of an interstellar object. Methane. That was not expected. It raised immediate questions about the thermal history of the comet's interior and the conditions in the protoplanetary disk where it was born. And then came the isotopes. In March 2026, Martin Cordner and his team published a paper in Nature that may turn out to be one of the most consequential planetary science results of the decade. Using Webb's NIR-SPEC instrument, they measured the ratio of deuterium to hydrogen in the water vapor surrounding 3I/Atlas. Deuterium is a heavier version of hydrogen carrying an extra neutron. The ratio they found was 0.98%, plus or minus 0.06. That is more than 30 times higher than the average measured in solar system comets. To find a higher D/H ratio anywhere in our solar system, you would have to look at the atmosphere of Venus, which has been altered by billions of years of extreme atmospheric evolution. In a comet, this level of deuterium enrichment has never been seen. The same paper measured the carbon isotope ratios. The 12C to 13C ratio in CO2 came back between 141 and 191. In carbon monoxide, it was between 123 and 172. Both ranges exceed anything found in the solar system, in nearby interstellar clouds, or in the protoplanetary disks around newborn stars in our galactic neighborhood. Those numbers are not just different. They belong to a different era of galactic history. Here's why. Carbon-13 accumulates in the interstellar medium over time, produced by successive generations of stars living and dying and enriching the gas around them. A high ratio of carbon-12 to carbon-13 means the material formed before that enrichment had time to build up. When the team compared their measurements against models of galactic chemical evolution, the numbers pointed to a formation time roughly 10 to 12 billion years ago. Our Sun formed 4.6 billion years ago. This comet may have been drifting through the galaxy for more than twice the entire lifespan of our solar system. The deuterium told a complementary story. That level of enrichment only occurs at temperatures below 30 Kelvin, which is negative 243 degrees Celsius. In those conditions, inside cold, shielded molecular clouds, deuterium atoms preferentially replace hydrogen and water ice, forming on tiny dust grains. Over time, those grains stick together into the building blocks of comets. The ice inside 3I/Atlas preserved that signature across billions of years of interstellar travel, locked away in the deep freeze between stars. Now let's talk about what is happening right now. 3I/Atlas is on its way out. It passed Jupiter's orbit in March 2026 and is accelerating back into interstellar space. It will never return. Every observation from this point forward is a diminishing opportunity. The Hubble and Webb telescopes have continued to track it as it fades, and the data collected during its passage is still being analyzed across dozens of institutions worldwide. But the window is closing. By the end of 2026, 3I/Atlas will be nearly 14 astronomical units from the Sun. By the end of 2027, over 26 astronomical units. If the nucleus is near the upper end of its size estimate, it may still be detectable by Hubble and Webb at those distances. If it is smaller, it will fade below detection within months. And after that, silence. We do not have a replacement mission. We do not have a spacecraft that can chase it. The next interstellar visitor could arrive tomorrow, or it could be years. We do not control the schedule. Here's what I want you to take away from all of this. A frozen fragment of another star's planetary system, possibly assembled before our Sun even existed, wandered through the galaxy for billions of years, survived cosmic ray bombardment, micrometeorite erosion, and the thermal extremes of interstellar space, and then for a few months in 2025 and 2026, it happened to pass close enough to our star for us to catch it. Not with our hands, with light, with infrared photons collected by a telescope orbiting 1 million miles from Earth, designed and launched by a species that has existed for a geological blink. The chemistry locked inside that object is a message we did not send for and cannot request again. It tells us that 12 billion years ago, in a colder, quieter corner of a younger galaxy, the raw materials for worlds and possibly for life were already being assembled. That the molecular toolkit is not unique to our solar system. That the universe has been doing this, building, scattering, delivering, for almost as long as it has existed. One comet, one pass, one chance to read the message before the silence returns. If this story stayed with you, subscribe and turn on notifications, because this is the kind of content I will keep making. Drop a comment letting me know what surprised you most, whether it was the deuterium ratio, the methane, or the idea that something older than our Sun just passed through our backyard. And share this with someone who needs to hear it, because this story deserves more than the silence it is getting.